In question 4a, we're told the photoelectric effect suggests electromagnetic waves can exhibit particle-like properties. We need to explain what is meant by threshold frequency and why the existence of a threshold frequency supports the particle nature of electromagnetic waves. Well, the threshold frequency is the lowest frequency of light that will eject electrons, whatever the intensity of the light. This supports the particle theory with the energy of a photon of light depending on its frequency, and with one photon being capable of freeing one electron. This is if the photon energy is greater than the work function, being the minimum energy needed to free an electron. With the wave theory of light, the energy depends on the intensity of the light, and so any frequency of light should be able to free electrons if the intensity is sufficiently high. A wave model would also require time for the electrons to absorb sufficient energy to escape, whereas no such time delay is observed. In B part 1, an alpha particle of mass 6.6 times 10 to the minus 27 kilograms has a kinetic energy of 9.6 times 10 to the minus 13 joules. We need to show the speed of the alpha particle is 1.7 times 10 to the 7 meters per second. Well, the kinetic energy is given by mass times speed squared over 2. Rearranging for the speed, putting in the values given in the question, gives a value of 1.71 times 10 to the 7 meters per second, which is around 1.7 times 10 to the 7 meters per second as required. In part 2, we need to find the momentum of the alpha particle. Well, momentum is mass times speed, and putting in the values gives 1.1 times 10 to the minus 19, the units being kilogram meter seconds to the minus 1. In part 3, we need to find the de Broglie wavelength of the alpha particle. Well, de Broglie wavelength is given by the Planck constant over momentum. Putting in the values for the Planck constant from the formula sheet, the momentum found in part 2 gives a wavelength of 5.9 times 10 to the minus 15 meters.